Hey, Abhinav, we are live on YouTube.
Right. Yes, sir.
Your voice seems to be very low. Just have it check on your mic.
Can you hear me now?
Yeah, I can hear you. It's good. Thank you.
Okay. Yeah.
We'll just wait for 2 minutes and let everybody join. We should start, right?
Yes, sir.
All right. So, hey, let's get started, Abhinav. So, by the way, welcome to all of you who have joined here for the today's session on lithium-ion cell 1D modeling. That's basically equivalent circuit-based modeling, and also electrochemical modeling methods of lithium-ion cell. So the whole objective of this webinar is to kind of give an overview on why do we actually do the modeling of lithium-ion cell, and what are the different approaches are there through which we can model cell. Then what are the kind of complexities in any of them. Also, kind of brief overrun through the models that our team Decibels has built. It would be one RC circuit based Thevenian model or the basic ring models or any other such kind of a models. So this may not be a session where you can just learn everything from basics like electrochemistry and stuff like that. So absolutely, you may have some knowledge about the cell and its its functioning, its working, and everything. So this program can give you the perspective of modeling a cell by using a software tools, right? So we have Abhinav today to make this session happen. Abhinav, over to you to take care of the rest of the session. Thank you very much.
Thank you, sir, for the introduction. Good evening, everyone. I'm Abhinav Arvind. I work at Decibels Lab as a patch algorithm development engineer. And today I'll be delivering this discussion on lithium-ion cell 1D modeling and electrochemical modeling. And we'll be briefly discussing on the modeling approaches for the respective. So today the agenda will be to start with the categorization of the cell behavior. So first we'll categorize it as linear and then non-linear behavior, and we will look at some examples of the same. And we will also talk about the another example in which we talk about the effect of discharge current and temperature on the lithium cell behavior. And then we will talk about the cell testing in real time with using the battery testing equipment, also called as BT, which is actually taken from the Aether testing laboratory. And then finally, we will come to cell behavior prediction with the two modeling approaches that we see here. One is the equivalent circuit model approach, the other one is electrochemical model approach. And then we will look into two of the prominent models that we have here developed at Decibels Lab. The first would be the RENT model, which is the most basic model that the battery can be represented with. And then we have the Thevenin 1RC model based on Thevenin laws. And this is a first order model, which is an advancement of the RENT model. So proceeding to cell behavior, so we can categorize this as two basic behaviors, that is linear and non-linear. So linear is a very simple representation of how a cell would behave, a cell system would behave in any situation. It's just a direct relationship between some of the parameters, and you don't have that much of a variation, and the entire system can be like represented as a simple equation like this. So using this linear behavior, you can't really estimate the complete the performance of the cell in real life, nor can you subject it to any dynamic situations or scenarios. So while linear situations do give you a brief idea of how the parameters would function with respect to each other, it doesn't give the complete picture. In real life, you have non-linear behavior, which is most likely always the case. So which is where the complex functions are introduced with variables. And these nonlinear systems are usually a little bit more complex to analyze. So if we can just take an example over here. So here we have on the left side a linear behavior between two parameters of the cell, the state of charge and the voltage. And here you can see it's just a simple linear representation here. This can just be expressed as a simply a line equation, and then the whole the complete analysis can be done only surrounding that equation. But it doesn't give the complete idea. But in realistic scenarios, you have the same two parameters, but then you have a non-linear fluctuation here, the non-linear representation, which is like a more complex and more non-linear in nature. So comparing these two, obviously we can say that it is more tough, more complex to have a in-depth understanding of the nonlinear behavior of the system, which which requires some more complex modeling approaches. So another example that we can have a look at would be the effect of temperature and different currents on the voltage graphs. So here we can see the graph on the left side would represents the depletion of voltage with the battery capacity at different currents, the different currents being drawn. So what this represents is that basically this relationship here cannot really be represented just using only equations, and you have to have a complete understanding of the system, how it works, model it using different software, and then come to a conclusion on how they would behave at different situations using at different parameters and in different environments, different situations. So this particular variation, this non-linearity, this non-linear behavior is what calls for the need for modeling of this particular system using 1D software such as MATLAB and Simulink. Now, also taking into account some of the relationship between parameters and some of the other situations that we have, such as the effect of discharge and charging current and discharge and charging temperature on the chemical reactions that occur within the cell, and also when we try to analyze the cycle count. So cycle count is basically the charge and discharge cycle. So once you charge it and then discharge it, that's one complete cycle. So analyzing this and trying to see what effect it has on the chemical reactions within the cell is really important. It has to be accounted for when you're trying to analyze the complete behavior. And then we have variation in the atmospheric conditions. So for example, if you have changing temperatures, or if you have changing pressure, and if you have changing chemical environments. Uh, so changing in these atmospheric conditions, even including humidity. So all of these parameters affect the reactions within the cell, and they affect the performance and the behavior of the cell. So all of these have to be taken into account. Now we are even the physical abuse. So for example, this comes under the mechanical conditions. So where, for example, we have impacts, shocks, vibration, and even some damage to the cell. So how will all of these parameters, how will this affect the behavior of the cell? Uh, and coming to the chemical aspects, where we have the electrolyte life. So the electrolyte is basically the medium where ions are exchanged between the electrodes. So this electrolyte, over time, it starts to degrade, and that will develop a certain influence on the chemical reactions and overall voltage performance of the entire cell, which also would be this. It would also lead to another consequence called electrode corrosion, because as electrolyte degrades, even the electrodes will also start to degrade, and over time, their ability to diffuse the ions will also reduce and will lead to corrosion. Uh, and also we have something called as solid electrolyte interface formation, which basically means that over time, when the electrolytes start to degrade and when the electrolytes start to degrade, we have basically a solid material that is deposited on the electrodes, and that can actually interfere with the reactions occurring within the cell, and that would lead to dendrites formation, and that dendrites formation is actually a dangerous condition which can lead to like a short circuit and then even like burning of the cell. Uh, and then we have unwanted chemical reactions, or also called as side chemical reactions. So with the main reactions occurring at the electrodes, there are undesired and unprevented chemical reactions that can occur. And these reactions also influence the way the cell would behave in real life. The change in the voltage, or the change in the current, the profile, all of these are it's completely affected by these side reactions. And finally, we come to the electrolyte and electrode aging, which is the aging of the entire system as a whole over continuous cycling, as we talked about here in point 3. So complete charging and discharging cycle would result in the complete system aging. So all these parameters that we talked about here, this complete list of parameters, these points, they are highly nonlinear in nature, and analyzing them in a just in a linear way, in a linear fashion, is not enough. Which is why we have the need to model all of this in a software, and try to bring about the complete understanding of the cell and its behavior in real life. Now, one of the methods in which cell behavior can be predicted would be to test it in real time using these battery testing equipment that we have here. This is from Aether. It's from the Aether laboratory. And here we have battery testing chambers and shelves in which like multiple cells are kept, and they're subjected to like various different tests and performance aspects, like different temperatures, different current, different chemical environments, different pressure, different humidity, temperature. All of these parameters lead to a lot of complicated procedures, which takes a lot of time. It's tedious. It takes the installment cost of these devices is quite high, including the operation cost. And those are some of the limitations of this testing equipment that we have here. Another thing is that when you're usually trying to test cells, they can be tested in bulk quantities, which means that if you try to say analyze the performance of one cell, one individual cell, it's not really feasible using this particular testing equipment, this test bench. So, which is why due to these limitations, we we use this particular approach called equivalent circuit approach or equivalent circuit model, ECM. And how we use that approach, we can just have a simple understanding of that using a simple mechanical system here. So here we can draw like an analogy or like a relationship between like a mechanical system and its electrical equivalent. Basically, that means that this mechanical system can be represented as an electrical system using these analogy. So when you consider a mass spring damper as a simple example, you have a mass which can be represented as an inductor. So mass is mechanical energy, kinetic energy, and then inductor is magnetic energy, and then spring, which stores energy and which can be represented as a capacitor that stores electrical energy, and the damper is acting as it basically damps or slows down the motion, and that can act as a resistor in the electrical equivalent analogy. So similar to this analogy that we established over here, we can establish an analogy between lithium-ion cell, the internal components of the lithium-ion cell, and its electrical equivalent. So when we talk about the internal components, we start with internal wiring, which is basically the ohmic resistance can be represented as an ohmic resistance. The chemical reactions that occur at the electrodes, they can be represented as chemical resistance. And then we have the chemical energy stored within the cell, and that can be represented as the capacitor. And then we have the electrodes. So the electrodes, they act as the voltage source or the voltage supply. So from this, we can just get a basic understanding of how electrical equivalent modeling is done when we look at a lithium-ion cell. So now now we proceed into the modeling aspect. So on the left-hand side, you can just see a simple representation of the equivalent circuit approach. So basically here you can see that at the voltage source here, this is the electrode over here. And then we have the resistors and capacitor, which represents the chemical part of the battery. And then we have the resistor here, which talks about the ohmic part, the ohmic resistance of the cell. And the whole circuit is then connected to a load. So here, so just in the equivalent circuit part of the approach, I will be introducing the RINT model, also called as the internal resistance model, and then the Thevenin 1 RC model, which is based on Thevenin's equivalent circuit approach. Now, to understand basically how we approach this particular method, we first have to understand how it is that we choose the right model for understanding the behavior of the cell. So, whenever we try to choose a model, there are three characteristics that we have to consider, right? So the first one would be the model complexity. The second would be the model accuracy, and then the third would be the simulation runtime. So all these three are interdependent, and it is very important to choose a particular model with the good balance between these three features. So let's consider a scenario where you have like you require a very high accuracy, which means higher accuracy would mean that you're trying to represent real life behavior of the cell. So if you have high accuracy, it means that your complexity also increases, and so does your simulation time. That's the advantage, is that while it is very accurate, building the model and analyzing it will become very complex, because the accuracy leads to involvement of many equations and many parameterization. It will also involve a lot of cost, time to build, and its complexity is just very high. It may not be feasible in all situations, but the main advantages is that it can represent the actual real life behavior of the cell. In another scenario where low accuracy is considered, you have lower complexity, and then you have lower simulation runtime. So in this kind of a situation, you can't really represent real life behavior of the cell. You can have acceptable levels of accuracy or acceptable levels of complexity, but you may not always be able to get the real life behavior of the cell, simply because they may have some missing parameters or some parts which are just left out, or some model simplification which has to be done in order to reduce the complexity. So keeping this three in mind, the model complexity, accuracy, and runtime, let's now look at the first approach that is used, which is called the RINT model. So the RINT model is basically a very simple linear model. It's a very simple representation of the cell as an ideal voltage source, which is connected in series to a resistance, an ohmic resistance. So that's basically what this RINT model is represented by. So in this particular entire circuit can just be represented by one equation using Kirchhoffs voltage law, and that we can see in the next slide. So yeah, in this particular slide, you'll be able to see the Kirchhoffs voltage law, how it is used to obtain the final voltage at the battery terminals, or what is also called as the load voltage. So Kirchhoffs voltage law is like, it just simply states that you have in a circuit, the net voltage is zero. The sum of all the voltage within the loop is zero. So if I form that equation, you get the summation of these two, the source voltage minus the voltage drop across the resistor. And on the right hand side of the terminology, you can see the parameters that are used in this equation. And so yeah, this is the most basic model that you can use. It's very linear. There is no non-linearity here. It's a very simple model to build. We have also modeled this in MATLAB and Simulink. Here is just a representation of the model in Simulink. I can just show that to you in my Simulink environment. So what you're seeing here is my Simulink environment right now, and in this Simulink environment, we have represented the complete RINT model and all the relationship between all of the parameters. So first, let's just have a look into this internal resistance model. So each block that you see over here is just are all the blocks that represent the relationships between each parameter of the model. So when we go into the internal resistance block, so yeah, here we have what is called as a lookup table. The lookup table is basically a table that is used to establish relationship between two parameters. For example, if I provide parameter input over here, then corresponding to these parameters, I have an output parameter over here. So that's what the lookup table is used for. And this kind of an approach is what we call as data-driven approach. So using these this kind of lookup tables, we have modeled the complete relationship between all of the parameters, and then we are able to get the full behavior of the cell. Like for example, in this we have the influence of temperature and the battery current on the state of charge. Here you can see another lookup table, which is basically used to establish a relationship between temperature and then capacity. So the output of this lookup table would be the capacity of the battery. So using this kind of an approach, using this kind of data-driven approach, we're able to get the full picture of how a battery would behave, and just determine how it would behave to different kind of inputs. And here we modeled the power loss based on the estimated internal resistance. So you can see here. So the power loss is basically based on ohmic losses, I squared R. So we are able to estimate the power loss using this using the internal resistance. And then we also have the open circuit voltage, which is nothing but the main branch voltage of the entire circuit. So here, even in this case, here we can see just the use of a lookup table. And here we have just the input of temperature and state of charge, the estimated state of charge. And then we have the output as the open circuit voltage here. And then finally, since all of these blocks are interrelated and they're all interdependent, so when we get the output from all of these these blocks. And finally, we are able to establish the relationship, the final equation of the terminal voltage, which is over here, which we derived using the Kirchhoffs Voltage Law, which we had seen in the presentation. So the final output here is the circuit voltage with the terminal voltage we see here. And on this part of the model, we can see the inputs that can be used. So the entire model uses one input, which is the battery current, and has one output, which is the terminal voltage. So this is just a brief overview of the Simulink model of the RINT model. And let's just have a look at the results that we get when we perform like a pulse current input to this. So so this pulse current input is basically just a simple discharge current and then a charge pulse current that we have given to the entire model. And this is basically just a linear input, a pulse charge and then a pulse discharge. So just to see how the voltage would be at the terminals of the entire model. So when we just observe the terminal voltage here, we can just see that there is just a linear drop and then there is a linear rise. So this is just a simple brief overview of the voltage at the output. So now when we discuss the advantage of this particular model, you can just say that this is a simple and linear representation. It just involves one equation that represents the entire system with very few variables, which basically means that when you build this model, it's pretty simple to build this model just using that one equation. So these are the main advantages, and that the simulation time required for this is like really low. So, but then the main disadvantages of this particular model is that it can only represent the linear behavior of the battery. It cannot be particularly used for representing the nonlinear behavior, which leads to low accuracy at the final interpretation. And it can also not be used in like dynamic situations with such a simple model, only because it's a linear representation. So that's just a basic overview of the RINT model. Next, of course, there are improvements on this model, and that the next improvement on this model would be the Thevenin model, basically which is called as the 1RC model or 1RC branch model. So the improvements made to the RINT model is that a pair of capacitor and resistor has been added to the circuit in parallel to this internal resistor that we have here. So basically what the purpose of building this particular model is to represent the chemical, the resistance, the internal resistance due to chemical actions. So we know that in a lithium ion cell, there are chemical reactions that take place between the anode and then the cathode, and even between the electrodes and the electrolyte. So these particular reactions produce certain amount, and that resistance is modeled over here in this particular branch of the resistor and capacitor. So that's basically what the purpose of using this particular branch is. So but here this particular resistor is for chemical reactions, and this capacitor is used to represent the chemical energy stored within the cell. So this particular the way of modeling, or this particular circuit, makes it a first order model, which we will see in the next slide. So here you can see, just have a brief overview of the equations being used for this particular model. So here we have one equation which represents the change in voltage across the capacitor in the RC branch, and we have one main equation that represents the final voltage at the terminals. And then on the right hand side, you can see here are the parameters that are used in the complete equation. So here we see that there are more number of parameters compared to the RINT model. And this we can see there is a model for this in Simulink. Let me just show that in the Simulink environment. So this is the Thevenin model, 1RC model. And here we can see that it's a bit more complex, where we have established some more complex relationships between each of the parameters to try to represent how it would behave in real life. So, for example, how we can see here the more complex relationship between, say, for example, the temperature and the open circuit voltage. In RINT model, it's a bit more simple, but in this, it's a bit more complex, involving two or more parameters used for estimation of the behavior. And then here we have the estimation of in the internal resistance on the similar way as to how we did it in the RINT model, but here we have a bit more dynamic situation happening within the lookup table, and here we also have an additional resistance being included here, which also influences the power loss. So this particular resistance that you see over here, this R1, is nothing but the resistance due to the chemical reactions occurring within. So upon analyzing all of this particular resistance, and this chemical resistance, the total power loss actually increases, making this model more accurate in terms of real life representation. So this power loss would then, of course, directly influence the temperature and then also the losses within the cell. And finally, using all of these, using all of this estimated parameters, we can just see here that the final terminal voltage is now also influenced by the current across both the voltage drop across the internal resistor as well as the chemical resistance. So all of this has a significant impact on the terminal voltage, which we will see in the results part of this model. So this is a brief overview of how the Simulink model is built of the 1RC model, and then we can just see its effect we can just see the effect of this model in the simulation results. Here we can just have a look. So when we give the same pulse current input for this model, we can just have a look at this terminal voltage output. So here it shows a little bit more nonlinear behavior. It's a little bit, it looks straight here, but it is actually nonlinear because of the exponential action of the capacitor. So that's basically what gives rise to this kind of a behavior, at the terminal voltage. So this is basically how we analyze the behavior of the Thevenin 1RC model. This can also be subjected to different kinds of input, not just the pulse input. It can be subjected to even like a simple drive cycle input where we have varying current inputs. But we'll not be discussing that now because it's a little bit complex. So when we talk about the Thevenin 1RC model's advantages and then some disadvantages, so we can just say that this particular model is it's a simple first order model which uses two equations and some more variables to model this. The resistor and capacitor relationship and the resistor and capacitor branch, which is included in the circuit, increases the accuracy of the model, which we saw in the terminal voltage graph. It has a slightly increased complexity compared to the RINT model, but it is still relatively low, and this model is simple and easier to build. But the disadvantages is that even though it considers some dynamic aspects, does not account for and it also does not account for so many other varying parameters such as cell aging, or electrolyte life aging, or self-discharge, things like voltage loss due to electrolyte aging and other unwanted side reactions that occur within the cell. So the conclusion between the first two models, the RENT model and the Thevenin 1RC model, here we can just say that the 1RC model is a bit more accurate. It is a bit more realistic, but it can use some additional improvements over the considered modeling approach. So of course there are some other improvements made to this to counter the the low accuracy. So the next one would be what we call as the PNGB model, and PNGB model is basically a much more advanced version of the Thevenin 1RC model. So in this particular model, we have an extra capacitor added in series over here, which you can see over here. It is called C0, and so basically the circuit is uses the same layout as the Thevenin 1RC, but then just includes this one additional circuit here, capacitor over here. So the purpose for including this additional capacitor over here is that it can actually represent some changing voltage within the circuit itself due to some other additional chemical reactions. So that is the purpose of this. It is to represent additional chemical reaction and the effect of it on the overall circuit voltage. It's still a first order model, but it includes an additional equation which is used to model the capacitor. So these are the equations on the left hand side, and on the right hand side here you can see the parameters that are used completely for modeling this particular circuit. So this is just a brief overview of the PNGB model. This is currently being researched. We are still building this particular model. We have yet to progress on this. So here when we can just talk about the advantages and disadvantages of using this model. Unlike the Thevenin 1RC model, this model actually accounts for certain variation in parameters, for example, in variation in temperature, variation in the state of charge, voltage, even to a certain extent the electrolyte life can be modeled in this, and you can show the slow degradation of that particular parameter in this. The additional capacitor can represent the change, or can show the change in the overall circuit voltage in this particular model. This is I would say this is a low to medium simulation time. It is slightly higher than that of the Thevenin 1RC. But on the disadvantages, we have that the additional capacitor that is used in this model can actually cause some inaccuracy in voltage readings. So basically, it is because if you try to look at an electrical circuit, you have a capacitor which acts as a filter, and the filter can actually it can change the readings in the voltage to a certain extent. So that can actually cause some accuracy errors within the circuit. And so another major disadvantage is that does not account for the cycle life, which we had talked about in the beginning of the presentation. So the cycle life is something that is it has to be accounted for, and that cannot be modeled using this particular approach. So overall, this is fairly accurate, but still not accurate enough to represent how it would behave in real life. So further improvements include the 2RC model, which basically goes along the same line as the Thevenin 1RC, but then here we have an additional RC branch. So basically what happens here is that it's apart from the chemical resistance that we had mentioned earlier, it also tries to represent what is known as activation resistance that occurs due to ion exchange. That particular phenomenon is a bit complex to represent here, but that particular phenomenon can actually be represented using this additional RC pair that you see here. So which makes this model actually very accurate and very close to real life. So that's the purpose of this model. So which basically includes the internal resistance or the ohmic resistance over here, the chemical resistance due to the chemical reactions, and also the resistance occurring due to ion exchange. So these three resistance put together makes this model actually a much more improved and a much more realistic model. So this makes it a second order model since there are two capacitors involved. And since these two capacitors are involved, we have two differential equations and one final equation that represents the terminal voltage. So basically, these are the model equations on the left side, and we have the parameters on the right side here. So again, here at Decibels Lab, we're currently working on these on this particular model. We actually aim to complete this model and have a brief and a good analysis and a realistic analysis of the cell behavior in real life using this particular approach. So, considering that this model actually is fairly accurate. So, so when we move on to the advantages and disadvantages, so actually it has a lot of advantage that it can very accurately represent the realistic behavior of the cell. And so, as I explained, it can account for three major types of resistances that occur within the cell. So, as I said, one resistance is the internal resistance or the ohmic resistance, resistance due to the wiring. The second resistance is the resistance occurring due to the chemical reactions at the electrodes, the anode and the cathode. And the third type of resistance would be the resistance due to ion exchange between the electrodes. So this particular model actually includes all of these three parameters, these three phenomena, which actually makes it a very good balance between the complexity, accuracy, and simulation runtime. So when you compare this to the PNGB model and to 1RC model, this makes it a very good choice for very good choice for completing the cell model, for going ahead with the cell model. So it has very few disadvantages. One is that it does not account for a particular phenomenon called as self-discharge. So each particular cell has something on a self-discharge. One good example to understand self-discharge would be that if you had a mobile phone and if you charge it to, let's say, 90%, and then you leave it overnight, you see in the next morning it has the percentage has dropped. It would be showing something like 87 or 88 percentage or something like 85 percentage. So that self-discharge occurs in almost all of the cells. And so none of the models till now include that particular modeling aspect, which is actually very important because this self-discharge can actually be used to analyze the cell degradation, the entire cell, including the electrolyte, the anode, the cathode, the interfaces. All of this will start to degrade over time, and that can be actually described using self-discharge. So none of the models, including the 2RC model, they are not able to model something called the self-discharge, which is exactly what is discussed in the next model. We will see that in what is called the extended PNGB model. So basically, the PNGB model is the same. The extended PNGB model is basically taken from the 2RC model itself, but one extra modification has been made to this. So basically, that extra modification would be that if we add two resistors in parallel to this particular setup over here, then this can be used to model the self-discharge of a cell in real life. So this addition is exactly what is used to counter the drawbacks between the previous models, which don't account for this. So this actually at this point, the complexity increases a lot, and just representing this using equations is not enough. And becomes so complex that building the model actually takes a lot more time which means that this model is not usually preferred. It is quite accurate, and it can actually represent a lot of dynamic behavior of the cell in real life. But it will not be feasible to build this model in real life because it's not really practical to use this particular approach. So while the advantage is that it can simulate self-discharge and certain other varying parameters, and it can represent very close to real life behavior, the added resistors and the influence of something called the self-discharge can actually increase the model complexity because it's a highly nonlinear model, and parameter estimation and then developing relationship between all the parameters within this particular model is kind of complex. It takes a lot of analysis and it takes a lot of time to establish all of the relationship and to understand the complete behavior. So that also would mean that the simulation runtime is quite high, which is not preferred. So overall, this particular model is not really a practical model, despite it having a very high level of accuracy. So when we come to the conclusion between all of these models, we can just have a brief look. So the RENT model, 1RC PNGB, 2RC model, and then finally the extended PNGB model. So the RENT is just a simple, basic, and linear representation, and it cannot be used for dynamic behavior and for nonlinear behavior, which means it can't be used for real-life analysis. In order to counter that, the 1RC Thevenin model was developed. So basically, in this model, it has an extra resistor and a capacitor to represent the chemical reactions occurring within the cell. So that chemical reaction can be modeled as a resistor, and that particular resistor adds to the actual cell degradation, and you can see the effect of it on the cell parameters when you subject it to different tests. It is accurate to a certain extent, but cannot be used in certain dynamic scenarios. It too is facing the same drawback. So the PNGB model is an improved version of the previous version, the 1RC model. It uses an extra capacitor to represent more accurate and dynamic behavior. But the drawback is that during simulation, the voltage reading, the voltage that will be finally shown at the terminal of the battery, will not be accurate because of this capacitor. It can cause some errors, which can actually reduce the accuracy of the battery finally. So even the PNGB model was improved into what we call the 2RC model. So this is basically an extended model of the previous versions that we have. So in this, it's considered more realistic because, as we saw, that it has an additional resistance. So basically, the cell has those three main types of resistances that occur within the components. So because of that, the cell performance is actually affected quite a lot, and that is something that is included in the 2RC model. And it's basically much more accurate than the first three models that we talked about. But still, one or two of the real life scenarios are not considered in this model, which is further tackled in the extended PNGB. So that extended PNGB model can be used to represent that scenario, which is called the battery self-discharge, the cell self-discharge, which we just had a brief example in the mobile phone. So when you use this extended PNGB, the model complexity is quite high. And you have to introduce even another approach in this, which we will talk about next. That particular approach makes it much more complex than all the models. So the last model, the extended PNGB model, is not really preferred in this kind of a scenario. So to conclude, when you compare all of this, we finally have to we conclude that it is concluded that the 2RC Thevenin model, the one over here, the fourth model, that is the most preferred because it has the most good balance between model accuracy complexity and runtime. So in terms of equivalent circuit model, that would be the model that that is most preferred over all the other models. So there is another approach when it comes to cell modeling. That particular approach is called electrochemical modeling, and this is the very specific type of approach which is it's a very restricted approach, and it is very specific to like a, a particular cell. Like it is highly dependent on the cell's chemistry. So for that reason, it makes it quite complicated. The main feature about electrochemical model is that it is used to represent the chemical reactions that occur at each electrode. So basically, these chemical reactions give an in-depth view of how a battery would behave at a molecular level. So that is the purpose of using electrochemical model. So if you want to analyze what happens at a molecular level, at an atomic level, and to analyze the complete chemical reaction that occurs within the cell. So for that reason, we use this particular model, this particular approach. So one of the approaches that we have is the simplest approach is called the Nernst equation or the Nernst model, which is the most basic model of the electrochemical cell. And some of the other more complex ones are what we call as P2D, or also called pseudo two-dimension model. It's a more complex, and SP model also is a further development on the P2D model. So just to give a brief overview of how the P2D model is taken. So basically, this is the P2D model. So here we have the electrochemical diagram, a basic diagram of how how an electrochemical cell is represented. So on the left-hand side is the cathode and right side is the anode. And in between, we have the separator filled with the electrolyte. So here we can see that there is a lithium-ion exchange that is occurring between these two. And this exchange can be represented in terms of differential equations, which are actually a set of several differential equations, which it makes up the entire system, the entire the reaction participants within this cell model. So the involvement of these complicated partial differential equations can actually increase the model complexity. But because of this, we're able to understand the complete molecular behavior of the cell. We're able to model its aging. We're able to model cell degradation, self-discharge, the effect of temperature, the effect of side reactions, the effect of unwanted chemical involvements, the effect of something called as dendritic growth, which is something that occurs when the electrolyte is not able to conduct ions anymore. So all of these nonlinear behavior can actually be modeled using the P2D model. And that P2D model is a very complicated approach because it involves a lot of equations. Many variables are involved, but it gives very highly accurate results. And this can actually be used in terms of research purposes, but cannot actually be used in real life. Like it cannot actually be implemented in a real life cell because it's just simply too complex. So to simplify this P2D model, another model was introduced, which is called the SP model, called the single particle model. So as I had talked about several variables and several equations being used in the P2D model, those equations are actually eliminated here in this particular model, which is actually simplifying the entire model to a set of just two equations, which makes the model very simple to understand. So consequently, the accuracy too reduces, which is actually a trade-off that has to be taken into account. It's either you have a very highly complex model with high accuracy, or you have a low complexity with low accuracy model, but you have a low simulation time as well. So all in all, the SP model is actually a simplified version of the P2D model. It is still a complex approach, but it is a much simpler version of the P2D model. And then finally, we have the Nernst model. The nurse model is basically is a very simple electrochemical model of a cell, which is basically used to establish an equation that describes the cell potential due to the reactions. So here you can see in this equation E cell, which represents the effect of the temperature, which affects. It also describes the effect of the number of reactants participating, and also we can see the effect of number of atoms that take place in the entire equation. So all of this entire equation can just give a basic representation of how the cell would perform, when subjected to these conditions. So this is just a simple representation. So the reactions at each electrode can be just analyzed, but complex like molecular processes cannot be studied using this particular model. If you have to go for like the complex molecular and microscopic study on how the cell would perform at that particular level, at a microscopic level, we have to use the P2D model, which is like very complex. So to summarize, let's just have a brief overview of the comparison between electrochemical and equivalent circuit model. So electrochemical models are very accurate on the whole, because they represent molecular level behavior, and at a very microscopic level, they're able to understand how all of the chemical reactions take place, and you're able to understand what is the influence of each reaction on the behavior of the whole system. It is, but on the other hand, they're very complex to build due to the number of variables involved. It has a lot of variables, and understanding each of the variables and establishing a relationship between all of these variables is very complex, and it is a very time-consuming task. And it was a lot of complicated differential equations which describe the whole system, which makes the model very complex. And building the entire model in any software actually requires a lot of time and requires a lot of understanding. And overall, the cost needed for building the entire model is actually is quite high. So in coming to equivalent circuit models, here we have a very simple representation of the cell as electrical components, which are easier to understand. The equations are less complex, and they follow set and defined laws that are easy to understand. Overall, lesser number of variables that are involved, and also the modeling complexity is lower, much lower compared to the electrochemical model. So when you look at these advantages that you have of ECM, equivalent circuit model, over the electrochemical model, it is sufficient to say that equivalent circuit model is the most preferred method, which is exactly what we are working on at Decibels Lab right now. We are working on the equivalent circuit model, and we are right now working on the 2RC model that we had discussed earlier. So here are some of the softwares that are used for simulating and even analyzing the behavior of the cells, subject to different kind of scenarios. So MATLAB and Simulink is exactly what we're working on at Decibels right now, Decibels Lab. Is, as I showed you, the two models, the RINT model and the 1RC model. We are using this system, this software, MATLAB Simulink, where we perform 1D simulation on the battery systems. We are also using Altair, Compose, and Activate, which is similar to MATLAB and Simulink. And we also use Scilab and XCOS. And then finally, COMSOL is another software that can be used, in which we can perform 1D and 3D simulation, where we can perform FEA, the thermal analysis of the battery, and many other complicated such analysis and simulations. So the final software here that also is used is something called Battery Management Studio, in which we can perform some additional simulations on it in real life time, and we can understand how it would behave in different scenarios. So with this, I would like to just conclude a brief introduction on how cell modeling approaches are introduced, how each one compares to another, and the relationship between model complexity, model accuracy, and simulation runtime. And to conclude that, I would say equivalent circuit model is like the best approach that that one would want to use if you want to like represent a battery in real life. So here are some of the references that we used for building the complete model, the models, and yeah, it's just this is yeah, this like yeah, I would like to conclude my presentation for this. Thank you.
Fantastic, Abhinav, greatly presented, and very happy to see through the whole details of the work that has been kind of presented. And there seems to be a fantastic audience on the other side. There are great questions, and we see most of the people staying back in the meeting here to sort of really attend the session and give time to go through all the details that you have presented. Fantastic. So glad for the presentation, and thank you very much, everyone. You've been a fantastic audience too, being on the other side. So if you have any queries, so please do put them in the chat box. And we also have Mr. Krishna, who is also our simulation engineer, who does support Abhinav for the team of activities at Battery Technology. We also not have Vinu today here, but he also contributes to the work on battery technology at Decibels Lab. So yeah, if you guys have any queries, so feel free to drop your questions. Abhinav, so over to you to address any of the queries.
Yeah, I would like to answer this one question by Mayur B. He has asked how to determine, verify the life cycles of the cell. So that is a good question. So basically what we do is we take the cell and we put it in the what is called the battery testing equipment. It's a hardware device in which like basically the bulk number of cells are put into the testing equipment, and they're run through basically a series of energy cycles. There is something called as energy cycle, and a series of energy cycles are used to determine over how many cycles, how much of capacity is lost. And deriving that kind of a test would be actually a very time-consuming test. And over that entire time, we get something called as the life cycle behavior or life cycle pattern of the cell. So yeah, that is how you estimate the life cycle. Am I audible?
Yeah, it is.
Right, sir. So yeah, that is how you determine the life cycles of the cell.
And there seems to be some more questions.
In external PNGB, why R0 is in parallel? We're actually looking into that. We're not like we're still trying to understand how the extended PNGB model is built. Yeah, we will actually get back to you on that. By using any kind of simulation, can we do the same? As that method is very time consuming. Which method are you referring to here, Mr. Mayur? No, this is actually very specific to energy cycle, because this is where we are able to get the complete influence of the internal processes of the cell and its influence over its entire life cycle. So that is why we use energy cycle itself. It's actually not just one or two energy cycles, it's a series of energy cycles, like up to 100, 200 different energy cycles of different profiles, which is actually used. There are modeling methods available for battery packs, but that would become actually a bit more electrochemical based. So where we use COMSOL. So that would also be possible. Hardware testing is also possible. So like there are drawbacks for both of them. The thermal aspect. So yeah, that's a good question by Mr. Nilesh. Yeah, so we use electrochemical model to understand the thermal aspects because you're able to understand the influence of highly dynamic thermal situations on the cell using electrochemical models. So it would be much more preferred when you're trying to do thermal analysis compared to equivalent circuit model.
Right. I think we might have addressed most of the questions. If any questions left, so
Yeah, there's one last question.
Sure,
Which type of lithium battery charges fast and long life discharging? See, how fast it charges and discharges is actually dependent on the chemicals being used inside, because lithium polymer as a whole, you have different types of chemical compositions, right? Your lithium polymer, you have lithium ion, your lithium manganese oxide, your lithium cobalt, your lithium aluminum cobalt. You have all of these chemicals. So it's dependent on how quickly the reaction can take place within the battery. That determines how fast it can charge and discharge, and also its capacity to handle high loads of current. So basically, it's just dependent on the chemistry that is involved. Yeah. So yes, yeah, I think the questions are done, sir.
perfect. Thanks a lot, Abhinav. So, by the way, thanks a lot for all the participants, and quite happy to see that enthusiasm and interest of such questions coming into the discussions. It's a great thing to see about the people who are interested in this area. By the way, we do have a lot of programs that we run at Decibels Lab, which kindly take care of areas of cell modeling, BMS modeling, advanced modeling of battery management system algorithms such as SOC, SOH, and things like that. So things are in great pipeline for all of you to learn. Not only just to learn the modeling, but also that we will be able to implement such algorithms into the real-time battery management system. So as always at Decibels Lab, so we would be making something which is very technically competitive for you to build your portfolios and profiles and that you can find opportunities in the industry. So keep us followed on all the places, LinkedIn, Instagram, and we will also open up the place where you can maybe join into the WhatsApp groups where you can where we can post you about the possibilities of discussions and anything that we kind of come across, some technical data sheets and stuff like that. We will send out maybe a link, and if that interests you, so jump into the group, and please feel free to contribute if you like to share anything that you have been working. So in that way, so we all grow the community of people across the battery technology. And by the way, we also build resources for the automotive sector in India to make it possibly achieve the dream of 2030 to migrate to all EV. So fantastic. So any questions that still left? Cell modeling and BMS is a right area to do a research as per Indian EV market. Nilesh, maybe just to address that question. So yes, there are companies currently requiring people who have a good exposure to cell technology, and it is definitely a good area to work on the research, because we also keep getting inquiries from some of the companies in the recent days that they want to train their employees and stuff like that on the areas of EV. there are few people who have started to develop their own BMS technologies in India too. So a lot of startups too, and then there are a lot of established companies too. So yeah, you need to have some solid exposure to electrochemistry, algorithms, control systems, and basics of C and stuff like that for the coding part of it, and some hands-on experience definitely. So that is something we can help you also with the courses at Decibels Lab. You can definitely do explore, but it definitely is the right area. Do we have inbuilt battery models in MATLAB, and hence why are we separately incorporating built-in ECM? Fantastic. See, definitely MATLAB already have Simscape models that are pre-built. So what happens is you do not know how and what approach have you used to build such models, right? So it is not always for an engineer. It should be a black box, right? So the idea here is actually to break down all of that to make it more understandable. And if you have to, or if you want to develop something more advanced from the continuation point of that, so you basically can build your own models, right? So those are something like, maybe you're just a beginner, have no knowledge about battery, but actually in a reality of the world, nothing just is so simple that, you just use a few blocks and assemble them and, make your a model completely working. There are a lot of practicalities that comes into a picture that makes sense to actually build your own models, right? You have total controllability about your model, and how does it predict, why does it predict, like that way. So considering that factor, it is wiser to build such models by yourself. So that's the way approach. And even in some cases, researchers and they actually write the codes even not using MATLAB too, because they have a total control over what they're trying to represent in terms of the models and stuff like that. Um, Simscape is definitely good for somebody who may not have an exposure to build the models or just to begin with. Great. So thanks a lot, Abhinav, again, for presenting the fantastic details. And thanks a lot, Krishna, for coming in for some questions to answer. Thanks a lot for you guys who have been here on this day for the session. Thank you very much again. We believe we met some of your expectations. If you have anything before you leave, so kindly do drop your feedbacks on the chat box. So it would be fantastic for us to make the future sessions on relevant topics. So never mind, just please drop some inputs and share the feedbacks before you leave. That would be really, really great. Okay, so waiting for your inputs on the chat box, guys. So by the way, yeah, thanks a lot again, everyone who are leaving, and so please do drop your feedbacks before you leave the meeting. Thank you very much again.
Yeah, thank you all. Thank you so much. Thank you, sir.
Thank you very much, Abhinav.
Yes.
But yeah, thanks a lot, everyone. Looks like it was very useful for everyone. So quite happy to see all of your feedbacks. Great. And if you would like us to add any topics in the future, so kindly do drop those topics too. So we would look forward to add such topics in the future.